Just wave if you can't hear me. Okay, so I'm going to summarize for you today transients in the local universe. And before I say anything else, I'm sure everybody knows what a transient is. It's something that goes bang in the night. And the main thing is what is local, and how do I define local universe here? So here I take my inspiration from a whole bunch of physics experiments coming online. The one most near and dear to your hearts is this one up here. And so essentially, if you think about advanced LIGO and you think about what I would call the guaranteed source from advanced LIGO, which is neutron-star mergers, I've been told by you guys that the distance to which you could detect neutron-star mergers is about 200 megaparsec. So as an astronomer, when I try to look for the light in the sound or the electromagnetic analog to this gravitational wave signal, there are a whole bunch of things that come to mind. The first thing that comes to mind is a picture is maybe complementary to the 1,000 words. Both more or less I'll leave to your judgment, but here's a simulation of a neutron-star merger, and here's the electromagnetic spectrum. And there are a lot of things you can learn if you can pinpoint the dot in the sky where you're detecting your gravitational waves from. You can learn about the local environment, the global environment, what does a host galaxy look like. If you get a spectrum, you can learn about the redshift, the chemical composition, velocities. If you have radio, you can see if there's synchrotron emission, so if there's relativistic ejecta. You can figure out whether it's hot, and overall just get a sense of the energetics of the system. So finding the light in the sound is a fun thing to do, but it's not easy. And what I want to tell you guys about today is that in search of this electromagnetic analog to a gravitational wave signal, astronomers also need to do a lot of work. I mean, you guys are doing the difficult part of making the gravitational wave piece of it work, but even to find and pinpoint this electromagnetic analog, the point I want to make today is that there are two major things that we need to do. First is in this relevant distance horizon, or in this local universe as I defined to be 200 megaparsec, we need to understand all the different types, all the different variety of explosive phenomena, of all the different types of transients, basically build an inventory of transients in the local universe. And the second thing, which is much more of a practical matter, just to make this search more tractable and more feasible, is a complete census of galaxies in this, again, in this distance horizon of 200 megaparsec. So there'll be two distinct pieces to this talk. So part one, which is the inventory of transients. So back when I started my thesis in 2005, it seemed that astronomers knew a lot about transients. They knew about two types of transients, novae and supernovae. This is thermonuclear supernovae, these are core collapse supernovae. But if you put them up on a plot like this, so let me just explain, since there are plenty of physicists in this audience. This is luminosity. It's just another way of luminosity on a log scale, another way to represent luminosity. And this is characteristic time scale. So how long does the transient last? Okay, so on this plot you see that classical novae and supernovae occupy very distinct regions, and there's a huge gap. There's a lot of white space in this plot. Now, is this just an accident? Did nature design this gap to be this way? Or do we actually expect something interesting to live in this gap? So let me tell you the first thing. The universe is a pretty darn big place. And often when you make plots like this, you're plagued by observational bias. It turns out that novae and supernovae are just very easy to find. Now, one would ask, why are novae easy to find? They're so faint. The reason novae are easy to find is because there are lots of them in our galaxy. Just in our own galaxy, there are about 20 per year. So if you just take two galaxies, there you go, you have your sample of hundreds of novae in just a few years. And supernovae are easy to find because they last for months, and they're a factor of 1,000 brighter. So with a small telescope, you can probe a huge cosmological volume, and it's pretty easy to find supernovae. So this white space is also something which is just hard for observers to look in. And are we the first to notice this gap? Not really. I mean, this gap was noticed way back. This is a picture of Edwin Hubble beside the Palomar 48-inch telescope. And yes, he is smoking a pipe. But that is no longer the case. Smoking has been banned from the Palomar 48-inch. In fact, human beings have been banned from this dome because we've roboticized this telescope. But you'll hear more about this telescope a little bit later. So what are the what do the theorists have to say? I mean, do we expect astrophysically, expect transients in this gap, transients with this intermediate luminosity between novae and supernovae, and timescales shorter than a month? So it turns out there's a whole bunch of very exotic theoretical models which are very simple predictions of stellar evolution that you expect to see transients in the gap. So this one here is of most interest to the audience here, which is coalescing neutron stars. So Brian Metzger had a very nice paper just a couple of months ago predicting the electromagnetic signature from this, and the luminosity is -12, smack in the gap between -10 and -16, and the time scale, the whole show is over in less than 2 days. There's also other ideas of the birth of a black hole. So the most massive stars, instead of collapsing into a neutron star, should collapse into a black hole. But if you have such a deep gravitational well, some of your ejector is going to fall back into the black hole. So your explosion itself will not be as powerful. It will be fainter and faster than supernovae. We haven't seen any good examples of this yet, but maybe I have a few. And then there's white dwarf models. This could be of interest to LISA. These are AM-CAN-WAN systems that merge, or accretion-induced collapse of a white dwarf. So this is just an overview to give you a sense that there is a lot of theoretical expectations of very, very basic stellar evolution that should give you transient phenomena that is in this luminosity gap. So putting on my observer's hat again, how exactly do I do better than previous nova and supernova searches to be sensitive to these transients in the gap? Now I have the worst of both worlds, right? Because not only am I looking for things fainter and faster than supernovae, I'm looking for things that are very, very rare. Yeah, the slides are also transient. Okay, so I'm also looking for things that are very, very rare. So how do I maximize my odds of finding these transients? Now for faint and fast, I need to image the same area of the sky at much higher frequency. So that's the fast cadence. I need to go deeper than supernova searches, so I'm actually sensitive to these faint events. And then I'm restricted, given current telescopes, to this local universe, because further than that, I won't see these faint events. But luckily for me, the local universe is very clumpy. Most of the light in this 200 megaparsec horizon is concentrated into galaxies and galaxy clusters. And if I just cherry pick those areas in the sky with lots of galaxies and lots of galaxy clusters, I can have a good shot at designing this type of a survey. So there are 3 surveys, of which I'll only talk about 2 today. One with the Palomar 60-inch and the other the Palomar Transient Factory. So you can see basically the progression was to do small projects, just take the 16 nearest galaxies, or take the 2 nearest clusters. This is the Virgo cluster and the Coma cluster, because the density there is something like 50 galaxies per square degree. So this is 500 galaxies, or do something that is, and we still didn't find anything. So what we really needed was something that was as large as 20,000 galaxies to be imaged every night at a reasonable depth in this local volume. So how exactly do we go about looking for transients in the sky? Let me just give you an example. Here's the beautiful M82 galaxy. This is a starburst galaxy, just 3.5 megaparsec away. And I'm going to zoom into this green box here. See, here's an image the Palomar 60-inch took on November 18th. Here's an image taken about a few days ago. And then you just do A minus B. Now this A minus B is not what you learn back in first grade, you know. It is a little bit harder because the weather is a little bit different and there are lots of small technical things. But if you do A minus B, even though these images look pretty identical, but before that you see a nice bright dot. And indeed that dot is the transient. In this case it turns out to be a very red nova in this starbursting environment. We've never before seen a classical nova in a rich starburst galaxy. So for people who are interested in classical novae, this was a pretty fun discovery. And then, okay, I looked at 60 galaxies every night for a year, right? 60 is a very, very small number. But I looked at them every night, and I looked at a depth much deeper than previous searches for classical novae. So what did I find? So in gray here are previous searches for classical novae. All these gray dots basically resemble novae in M31, our galaxy. And these green circles and stars, and those are just technical details about the differences between these novae, are the ones that I found with the 60-inch. The first thing that jumps out at you is that this gray relation here, This is again the same plot, by the way, luminosity as a function of time scale. So the first thing that should jump out at you is that this gray relation here, which people have talked about a lot in the literature in the past few decades, it's called the maximum magnitude rate of decline relation. Essentially, this relation tells you that classical nova physics should be governed by one parameter, only the mass of the white dwarf. The more massive a white dwarf, the brighter the classical nova should be, and the shorter lived it should be. Actually, I'm not sure if everybody here knows what a classical nova is. So classical nova is basically a white dwarf and a red giant, mass transfer, little bit of mass transfer from the red giant onto the white dwarf that initiates a thermonuclear runaway, and so some of this material burns. Now if you make the white dwarf more massive, you'll get a brighter explosion, and it will last for a short amount of time. But what we ended up finding with this survey was a whole bunch of novae which spectroscopically looked exactly like classical novae, but photometrically lied in this very strange region. So maybe this relation was not as simple as we thought, and this population is really telling us that nova physics, classical nova physics, is much richer than this one parameter family which depends on the mass of the white dwarf. In fact, what we think is happening here is that these are very, very hot white dwarfs. So if the white dwarf is very, very hot, then a small amount of matter would give you the critical pressure you need for thermonuclear runaway and give you faint and fast novae. And here's a theoretical model which confirms exactly what I just said, which doesn't pay heed to this one parameter and tries to take 4 parameters in classical nova models to reproduce novae that we find. All right, but 60 galaxies is very, very far from what we need to be sensitive to these faint and fast supernovae, what we originally set out to look for. So hence we...
The red dot. Yeah.
That one? That's also a classical nova, but it was extremely red, and basically the G minus R color was very, very red at maximum light. So it was very extincted. This is actually one in M82, one of the starbursting galaxies, and we don't have spectroscopic confirmation of this one. So this one I think is just plagued in a lot of dust, and that's what made it so red. And so the correction that you make to put that dot up there is what makes it unusual. But we don't expect this to be very different from the usual classical novae. At least we don't have enough evidence to prove that this is very different from your generic population. Okay. So the next survey I want to tell you guys about is the Palomar Transient Factory. Now one of the things that, looking for these transients in the local universe, these transients in the gap, was one of the key drivers of this project. Because if you look at the local universe, there are a ton of galaxy clusters and local light concentrations that you could cherry pick and look at in order to do this search very, very effectively. So let me just give you a brief introduction of what is the Palomar Transient Factory. So the Palomar Transient Factory is a wide-angle, high-cadence search, and it was designed with just one goal in mind: to systematically chart the night sky to look for optical transients. Now we were very serious when we put in this term factory, because what we wanted to do was not just a one telescope system, but do a start-to-finish project. Not only find the transient, but unleash an arsenal of follow-up telescopes to understand the physical nature of the transients that we find. So basically the two main workhorses are the Palomar 48-inch telescope. That is a discovery machine. On this we took an old camera. This is a very old telescope. It's done the Palomar Observatory Sky Survey, for those of you familiar with that. And basically we took an old camera from the CFH3 telescope that they were no longer using. We put it on this telescope, roboticized it, and we had a large field of view camera, an 8 square degree camera. And we decided that we're going to do this search with only one filter. So usually many of these searches have multiple filters so that you get color information. But what we did was one filter, large field of view, just maximize the total area on sky that you can cover and the cadence with which you can cover that sky. And then as soon as we find a dot, a new transient with this telescope, we automatically send the coordinates, the RE and DEC, of the transient to the Palomar 60-inch. And the Palomar 60-inch, which has a very small field of view camera, but is a little bit bigger telescope, goes and gets color information. So it gets G band, R band, I band, basically spans the optical spectrum and takes 3 filters imaging to get color information of this transient. Now, once we have both the discovery and the classification, this actually now happens in less than 10 minutes. All of our pipelines are completely automated and the two telescopes are completely robotic. Then we unleash on it the arsenal of telescopes. We make sure that we get a spectrum of all the dots that we find, especially if it's in the local universe. In local universe, we are complete in getting spectroscopic confirmation of each of these dots. And then if it's interesting, then we point the Swift satellite to it, get X-ray and UV information. We also have an EVLA program to get radio information, but essentially try and understand the entire electromagnetic spectrum of these transients. So with the survey of this nature, it's a pretty big survey, and there's a ton of science that you can do, both galactic as well as extragalactic. But my thesis project is essentially, I'm going to focus on these two projects here, and on this slice of the pie. So essentially this is the one-day cadence experiment on 20,000 galaxies. There are a bunch of other experiments that also are part of the Palomar Transient Factory, but that's not, that's the subject of a different talk. So basically what have we found so far? Now, by design, this experiment is the most sensitive experiment to date to find transients in the gap. And so far, in the past 1 year of operation, we have found 125 transients. And these 125 transients are mostly supernovae, which is not a surprise, mostly core collapse supernovae and type 1a supernovae. But there is a thin slice of the pie, just about 11% of the total number of transients in the local universe that we have spectroscopically confirmed. That is very, very interesting. It is unlike all the classical novae and all the thermonuclear and core collapse supernovae that we know of. So I'm going to tell you a few of these interesting transients that we have found in the gap so far.
Sorry, why just finish telling us about all the novae? There's no novae in this file.
Correct, because most of the novae are actually in M31, because novae are so much fainter, and M31 season is just starting. We didn't really do M31 last season. So in the next few months, we're going to have a substantial, there's 2 novae that we have so far, which is just too small to bother plotting. Okay, so the first interesting transient that we have found, this is actually just from last week, and it's PTF10HJZ. We just have a naming convention which goes through the letters. And in fact, last Sunday, we found this dot near this galaxy, which is only 20 megaparsec away. And the part that blows my mind is this light curve. So we found it on Sunday night. We found it again on Monday night. On Monday night, we got a spectrum. On Tuesday night, we got a spectrum. On Tuesday night, we got a spectrum with Keck. And this was supposed to be a 19.4 mag object, and the trace is really, really faint. So it turns out it had faded. And then it faded some more. And on this night, again, we looked at it with Keck because we couldn't believe a transient would just disappear on us like that. And sure enough, with 20 minutes of Keck imaging, when I draw an arrow, I mean upper limit, as in it was not detected. It decayed to fainter than 23.8 in 4 days. So this decay time scale is just completely unprecedented. We don't have any other examples of a transient that decays by more than a magnitude a day. So this difference here is, so magnitude is a factor of 2.5 in flux. And something decaying by, usually a supernova would decay by a magnitude in a month. And the fastest transients that we have known of, which is just a handful, decay by a magnitude in 10 days. This thing decayed by a magnitude in a day. The only thing that we know is that the spectra have no features whatsoever. It's a completely flat spectrum, no emission lines, no absorption lines. If it was a supernova, you expect some broad features. If it was a nova, you expect some Balmer emission. Even if it was a dwarf nova, you expect that you will see some H-alpha emission, but none of that. We also triggered the Swift satellite on it. There's no detection in UV or X-ray. We have no idea what this is. I mean, this is, our best guess right now is one of probably Brian Metzger's model, which was what you expect an electromagnetic counterpart of a gravitational wave signal to look like. That would be crazy, right? I mean, that would be an extraordinary claim, and we've only been working on this for a week, so maybe we'll find a better explanation, but this transient has completely stumped us. But if you guys found something in your LIGO stream,
How far away is that?
20 megaparsec. Well within the enhanced LIGO distance horizon. So if you guys want coordinates or a timestamp, just let me know. But sure. And no, this is the only thing like this that we've seen in the past year. I mean,
how certain are you that this thing is associated?
In terms of spectra, there's no line that tells us a redshift. So usually the way we get the nail in the coffin is if you have an emission line that is at the same redshift as the galaxy. But in this case, the spectra is completely featureless.
So
there's nothing.
Accidentally close to that galaxy.
Okay, so if it's accidentally close to the galaxy, there are two possibilities. One is it's in our galaxy, so it's something foreground, but the galactic latitude in this case is 40 degrees. And the galactic imposters that we know of, which is basically two types. One is an M dwarf flare, and M dwarf flares are usually very, very blue. And this thing, if you look at the colors, it's not blue at all, and the spectrum is not blue at all. So M dwarf flare is very unlikely, and plus at B of 40 degrees, the rates just crash because the rates scale with height from the galactic plane. Or our band. Sunday. So Saturday night, Sunday morning. I can give you an exact timestamp later. Last week.
Yeah, what's the scale of the picture?
This picture is about, let me think. This is about 200 arc seconds, so like 3.5 arc minutes by 3.5 arc minutes. But really, we're very, very stumped by this one. And we have a Keck spectrum, Keck imaging. We have 4 telescopes that confirms it, so it's not an instrumental thing. It's for sure real. And yeah, I mean, I really don't know. And the background possibility that it's a background supernova that just happened to be near this galaxy is also unlikely, because again, you expect to see some broad features. We know what supernovae at all phases look like, and supernovae don't die that fast. So. Keck is, I think, the biggest telescope.
Oh, you did?
Yeah, we have a Keck spectrum on this night. We have a Keck imaging on this night. This is as deep as you can go from the ground to constrain this event. And this is an upper limit. It was not detected by Keck 4 days after discovery. That is just unheard of. So, I mean, so basically, where do we go from?
Be very careful with the theoretical interpretation of this.
Mm-hmm.
And I would in particular be very careful to not adopt a model that predicts such a path.
Sure.
Predicts the path.
Sure. So there should be more models out there. People need to come up with ideas of what would disappear so quickly. I don't know. So there should be other models. I mean, this is just crazy. And the luminosity of this transient is -12. So it is again intermediate between novae and supernovae, because the gap is from -10 to -16. So anyway, something very, very interesting just from last week. So our next step forward is to basically go hunting for a host, go and see if there was something under this dot after this explosion has gone away. So we're going to get very deep Keck, and if Keck doesn't do the job, then Hubble imaging to basically find out if there was a dwarf galaxy that was just happened to be at that position, or a star, or anything that could give us a clue on the host. And if there's nothing there, then this must be associated with this galaxy. No, we didn't really expect anything relativistic, so we didn't trigger EVLA. But yeah, that's a regret. We should have. It doesn't look like a star. I mean, if that's what. So basically, it has no match in any stellar library. If it was not a transient, I don't know. It doesn't look like a star. Doesn't look like a galaxy. So I don't know what to say. So, but the continuum is solid. You see that there is a dot in the slit, and you see the continuum, just no features. Okay, so let's go back a month now instead of a week, and let me tell you about another transient, PTF10FQS. This was a luminous red nova. Some of you probably saw the paper on this just 2 weeks ago. This is in a beautiful face-on spiral galaxy in the Virgo cluster, and this dot here is the transient that I'm going to talk about. Here the spectrum is very clear. There's a very narrow Balmer emission. There are these forbidden calcium-2 lines, and calcium H and K, calcium-2 IR, maybe even a broad feature under this, and we've seen this type of thing before. It's very, very rare. We only know of a total of 4 examples in all of transient studies that look like this, but we at least have one more example of what this transient is. But because it's a rare transient, we unleashed all possible follow-up on it. We took a radio image with the EVLA, nothing there, to a limit that is fainter than the faintest supernovae of either type. Nothing in the UV imaging, so it's not a very hot source. Nothing in the X-ray imaging, it's probably not associated with a neutron star black hole, so I guess you guys don't care too much about something like this. But we also try to look for progenitor of these type of events. So it turns out M99 is such a pretty galaxy that people do all kinds of star formation studies of these galaxies. So in the Hubble and Spitzer archives, there was pre-explosion imaging. So we could go back into the archive and see if we could identify the star that actually exploded. Now if it was a core collapse supernova, then we would see a blue supergiant or a red supergiant, depending on the type of the supernova that would be at this position, but we see nothing there. Even in the Spitzer imaging, this is in the mid-infrared, we don't see anything there. So this is unlikely to be a star more massive than 10 solar masses that exploded, because at the distance of M99, with this depth, we should have been able to see something. Now I told you there were 4 of these guys, right? So here is a progenitor of all 4 of them. The 2 that were even nearer than the Virgo cluster, both of these were actually discovered in 2008. We did detect this mid-infrared progenitor. So we detected a very, very dusty red AGB type of asymptotic giant branch type of star that looked like it exploded, at least in these 2 cases. And in these 2, the upper limits are consistent with these luminosities. So putting this picture of pieces of all the different parts of the electromagnetic spectrum together, there's a debate going on in the literature of exactly what was the mass of the star that exploded in this case. Some people claim that if you just look at the explosion signature, just look at the spectrum, it could be a luminous blue variable. This is actually this is a Hubble image and trying to look at the age of the stars surrounding the explosion and estimating the mass of the star that exploded. But I think both of these are very, very unlikely, because there is no blue supergiant, there is no red supergiant at the position of the source. And in fact, I think this group of transients, which is now a group of 4 transients, is mapping our island of ignorance. We know what happens to a star when it's more massive than 10 solar masses, or 11 solar masses. People argue about this threshold. But we know that it will become a core collapse supernova, and we know what a core collapse supernova looks like. And we know that when a star is less massive than 8 solar masses, you'll get a white dwarf. But between 8 and 11 solar masses, especially stars that are so red, this is an HR diagram, so like luminosity as a function of color, these 2 transients fall in a very empty region of this diagram. So if you have a very, very red AGB star, there's a very nice paper by Todd Thompson suggesting that this is electron capture in an AGB star. So this is just an example of how we put together the different pieces to understand the nature of the explosion. So changing gears again and going on to yet another example. This is PTF 09DAV. So we went from last week to last month to one from last year, which we still haven't figured out. Now this was a transient where the transient is actually very far from its putative host galaxy. We took a spectrum of this transient, and the lines are at the same distance as this galaxy. But the scale on this plot is that this distance here is 10 kiloparsec. So this dot is actually 40 kiloparsec away from its putative host. Now that's really far. You guys know the size of the Milky Way is. You expect everything, all the action to be within 30 kiloparsec. 40 kiloparsec is just really, really far from the center of the galaxy. In terms of the photometric evolution, this was again a transient in the gap. Its peak absolute magnitude was about -15, and it decayed quickly, and quickly in this case was 1 magnitude in 10 days. This is already faster than that. This already puts it at the fast end of all supernovae, and this is an order of magnitude slower than the first example that I showed you, which was 1 magnitude in 1 day. And this transient was very red and very peculiar spectroscopically. So spectroscopically in 3 months, basically we became completely transparent to the ejector, and we could see right through it and detect this H-alpha emission. So usually people who do think about explosions look at an H-alpha nebula line and say, this must be from a massive star wind interacting with the circumstellar environment, and that's what's giving you the H-alpha emission. But how do you get a massive star to be so far away from its host galaxy? It's too young to make its way 40 kiloparsec away, even if you give it hypervelocities or make it go really, really fast. So something about this picture is not holding together. And in fact, this early spectrum shows that it looks like a thermonuclear supernova, a white dwarf and a red giant. So all the different pieces of this story don't really hold up together into one simple type of, into a variant of a supernova explosion, I should say. There are suggestions that this might be a 0.1A supernova, which is a merge of AIM-CAN-MAN systems, or accretion-induced collapse, or some other new physics that we don't fully understand. So we're still getting more follow-up data to really make sense of this event. And I'll tell you more when I know the answer. Your suggestions are welcome. Okay, so I've told you a bunch of disjointed stories of different types of transients that we have found with the Palomar Transient Factory. But this is the picture that I wanted to chart out in the past year. So basically, in the past few years, this is what the progress has been like. The stars represent transients discovered by the Palomar Transient Factory, and there are a few more dots that people have noticed that are also in this luminosity gap. So clearly this picture is starting to get filled in, albeit quite slowly because these transients are very rare. But I think on a time scale of the next 3 years, we should make progress on building this complete inventory of transients and understanding all the different types of explosive phenomena in the local universe. Because of time, I didn't tell you the story about this birth of black holes, but you can ask me about later. I didn't tell you about all the stars on this plot, but you can ask me later and I can tell you more about that. So this brings me to the conclusion of part 1 of this talk, which is that the fun of trying to fill in this phase space of transients has only just begun. So changing gears completely to part 2, which is I think the second important thing that astronomers need to work on to make the electromagnetic analog search possible. So this is a census of the local universe, just a practical matter. So before I dive into that, I want to tell you a little bit more about Brian Metzger's work, which was actually a solid prediction of what an electromagnetic analog would look like from a neutron star in spiral. So this is also a couple of other older papers that he draws inspiration from. But basically, his claim in the paper is that the electromagnetic analog to neutron star merger would be completely radioactively powered, and radioactively powered from our process elements. And this is basically the atomic mass of the elements that get left behind. And simply by fission and beta decay, you would get a light curve that would look like this. And these are the different filters in the optical band. And you can see this is a log time scale. So whatever happens to this transient, it's basically gone in a day. So it will be a very, very fast evolving transient. And this also motivates basically the depth to which we need to look for an electromagnetic analog. So the luminosities involved here are something like 10 to the 40 to 10 to the 41 ergs. And if you play it safe, you basically, in the numbers that I think of, which is this weird absolute magnitude scale, for enhanced LIGO, which has a 50 megaparsec horizon, we need to go down to an apparent magnitude of about 20.5, which means a 1 meter class telescope for imaging and a 5 meter class for spectroscopy. Something like PTF, that's good enough. If there is an analog that exists like this, we would be sensitive to it. Now advanced LIGO is a 200 megaparsec horizon. This is 3 magnitudes further in terms of absolute magnitude, right? In terms of the distance modulus. So we need to go down to 23.5. This already puts you at a 5 meter class telescope for imaging and a more than 10 meter class for spectroscopy. The only reason I'm putting these numbers out here is that in the advanced LIGO era, there is going to be, it's only the big telescopes that will be able to go deep enough to look for the analog, and resources are going to, we have to make the most of the resources that would be available then. So okay, so keeping this at the back of our head that we need big telescopes and there are very few of these, and we only have a day to do whatever we want to do to find this electromagnetic analog. Let's see how bad the problem really is. How difficult is the problem? So LIGO now operates at a frequency of 150 hertz. Even if you take the baseline of the Earth, which is basically 10,000 kilometers or so, lambda over d, back of the envelope, also gives you something like 11 degrees. So, and if you actually do this more carefully, so this is work done by Lynching Wen. You can basically, what Lynching did was she just took 100 points in the sky and computed what the localization would be if you assumed advanced LIGO, Hanford, advanced LIGO, Louisiana, and advanced Virgo, and gave me these ellipses on the sky to work with. The median of this ellipse is something like 12 square degrees for advanced LIGO and 50 square degrees for enhanced LIGO. Now I know Samaya is looking at this and saying, no, she's way too optimistic. Life is actually much harder than these ellipses, because Samaya has shown in her work that with her Monte Carlo Markov chain methods that the localizations are even worse, and there are actually secondary lobes and things like that to worry about. The geometry doesn't just constrain you to an ellipse. So anyway, this is all stuff that you guys are experts on, but taking this simple picture as a starting point, what does this mean? If I point a telescope in one of these ellipses to the depth that we just discussed earlier, what do I expect to see? So the blue here is enhanced LIGO, and the red here is advanced LIGO, and in a single snapshot, which is like for enhanced LIGO 60-second exposure with say the Palomar 48-inch in the entire aero ellipse, or for advanced LIGO with a 5-meter class telescope, just a few minutes, you expect to see hundreds of supernovae. These are hundreds of background supernovae that have nothing to do with your gravitational wave event. They're not even in your distance horizon. They're much beyond. They're background events. And you also expect to see hundreds of galactic events, which are M-dwarf flares, dwarf novae. Now trust me, with advanced LIGO, if these things are going to be in your last magnitude bin, they're going to be 23rd magnitude. Even if you have the 30-meter telescope at your disposal, you cannot take spectra of 100 transients within one day, or one night actually, because that's all you will have to confirm them before the true signal, which is something like what Brian Metzger predicts, would be totally gone. So this red box here should tell you there is hope.
Are you falling in any distance into it?
No, so this is just assuming the localization, spatial localization. And just a raw area on the sky, and the depth is the depth to which you need to be sensitive to Metzger's prediction. That's it. So there's no other information that has been taken into account here. So, okay, there's a haystack of false positives. You could go through it one at a time and pick out which one is real, but that'll take infinite amount of telescope time. So what you need is a magnet to pull out the goodies, right? And the magnet proposed here is a local universe galaxy census. So not using a distance estimate from the LIGO estimate, but saying that, okay, we know that if this was a neutron star in spiral, the sensitivity of LIGO is only out to 200 megaparsec. So in this giant aero ellipse, only the galaxies which are within 200 megaparsec could host the electromagnetic analog. So instead of the giant ellipse, now you're looking at little ellipses within it, where a galaxy exists, which is known to be within 200 megaparsec, and you're restricting all of your follow-up, all of your resources on this very, very small area inside this large ellipse. So if you have a complete catalog of galaxies in the local universe, that's it, you're done. So this problem here, which was hundreds of events, this is again a log of false positives, basically converts your square degree problem or tens of square degree problem to a square arc-minute problem. You expect a couple of events, that's it, that will accidentally happen to land on top of your galaxy. So this is a very, very tractable problem. If you have a handful of events, then even within a day you can unleash the entire band of the electromagnetic spectrum and really try and understand the physical nature of this potential electromagnetic analog. Okay, so the next thing that often people have asked is that you need a big telescope, that is clear. And now if you're only looking at specific galaxies within this aero circle, do you still need a camera with a large field of view, or can you just individually go pointing at each of these galaxies? So the answer is that if you just take again the simulation of these 100 ellipses and see what the number of galaxies looks like within these ellipses, this is just a cumulative plot, so this is a median, this is say the 90th percentile. it's still hundreds of galaxies. So it would be incredibly inefficient to go pointing at them one at a time. The local universe is actually very, very clumpy. So most of these galaxies come in groups or in galaxy clusters. So if you have a square degree type of camera with even 1 square degree, this search could be much, much more efficient by an order of magnitude or so if you had a large field of view camera instead of trying to point to the galaxy one at a time. Again, just a practical note, because this is a question that I'm often asked. So what are the telescopes that we're talking about that actually have a square degree like camera that are 5 meter class? They actually fit on this figure. There's not that many more. CFHT is a 3.5 meter telescope with a 1 square degree camera. This is again for advanced LIGO. Magellan has a mega cam now, which is also 1 square degree camera. And for follow-up, the biggest things we have right now, Keck and Gemini. These are 10 meter telescopes. This is an 8 meter telescope. And then these are things which may or may not happen by the advanced LIGO era, which is LSST for imaging, large field of view imaging, and say the 30 meter telescope for spectroscopy. The bottom line is it's really not a lot of telescopes. So having a severe and secure filter that reduces your false positives from hundreds to 1 or a few is very, very important. So do we actually have this complete catalog of galaxies that can allow us to do this? And the answer is no, not really, unfortunately. So I want you to focus on this dashed line. This is the completeness of the catalog as a function of distance. Now for enhanced LIGO, we are okay, we are about 70% complete. But for advanced LIGO, we are only about 50% complete. And in order to complete this catalog, which currently has 150,000 galaxies, to go up to 95% completeness, which is about 300,000 galaxies, we need an all-sky spectroscopic survey down to this apparent magnitude of 20. So as in an all-sky spectroscopic survey with again a 4 to 5 meter class telescope. This is not something that is straightforward. Most of the galaxies that we know about are clearly the biggest, brightest, nearest galaxies. And the ones that are missing are these fainter, smaller galaxies. But we just discussed that this catalog is incredibly important, and we really need this to look for the electromagnetic analog. So what can we do if we don't, if we can't put an all-sky spectroscopic survey? Is there something that we can do? So to motivate that, let me remind you guys of the spectra of galaxies. Basically, galaxies are of 2 types, red and blue. The blue galaxies have a flat continuum and a very important emission feature, H alpha at 65-63 angstrom. And then there's a red galaxy which doesn't have any spectacular features. Maybe there's a break difference here and here. But this feature here, which is so much brighter than the continuum, we can really make use of this fact and do what I would call a poor man's spectroscopy. If you think of, let me describe this a little bit better. So say at redshift 0, this H alpha emission line would be centered at 65-63 angstrom, and then by the time we go out to 200 megaparsec, the line would be redshifted. And this is a very significant shift. The shift would be something like 300 angstrom. So instead of 65-63, it would be at 68-63 angstrom. Now if we design very narrow filters, so filters that are just centered around H alpha between redshift 0 and redshift of 200 megaparsec, then we can have say 4 or 5 70 angstrom filters, and then you have a poor man's spectrograph. Because if there's a galaxy that is say not there in the first bin, there in the second bin, not in the third, fourth and fifth bin, we can say what a rough estimate to its distance would be, assuming that that thing that went on in the second bin and was off in all the other bins was this H alpha emission line. So if you do this type of a narrowband survey, so narrowband imaging is infinitely cheaper than spectroscopy basically. So again, it's a practical consideration because you can do this with a smaller telescope and it's easy to get the large field of view. So using the telescope that I'm most familiar with, which is a Palomar 48-inch, in just a 2-minute exposure, covering, and now assuming that it covers all sky, which it doesn't, it only covers the northern sky, so you'll need another one for the southern sky. But in a 2-minute exposure with this narrowband filter method, we can take the catalog from 50% completeness to 85% completeness, which is pretty significant given how rare the events that we'll be looking for with advanced LIGO are. And these are some more details on different ways you can estimate the completeness. I can go into that if you guys have questions. Okay, so but clearly if you're doing poor man spectroscopy and just this narrow band method, there are tons of things that could be that could contaminate your catalog. You could have some other emission line from some other background galaxy that happens to shift into your filter band, or some other strange things could happen that could contaminate your catalog. So this catalog would need some sort of quality control. So quality control can be done by taking spectra, which span the entire wavelength range from 3000 angstroms to 9000 angstroms. And here are just some possibilities of telescopes with large field of view cameras. This one actually hasn't yet been funded. This is Big Boss, which is on a 4-meter Kidd Peak telescope and very large field of view fiber-fed spectrograph. This is SDSS++. This is LAMOST, which is a Chinese experiment, again a 3.5-meter telescope with 5,000 fibers over a large field of view to actually do, to work towards completing this catalog. But this one is, according to our Chinese friends, is not delivering the promised sensitivity. The weather and stuff is really terrible on this site. So I don't know so much about this one, but here's, the Magellan is on a good site. They have, again, a large field of view spectrograph that they call IMAX, which could potentially not do the job of completing the catalog, but at least do what I would call the quality control on the catalog. Okay, so that's pretty much it. I hope I've convinced you that astronomers have a lot of work to do in the next few years as well to make this connection between the electromagnetic light and the gravitational wave sound. And the two things are a complete census of galaxies in the local universe and a complete inventory of transients in those galaxies. And that's it. I just want to conclude with some propaganda from the US government. The census is in our hands. Questions?
After 290 megaparsec, what fraction of the sky is either galaxy or within?
Very, very small, less than 0.1% or so.
Less than one.
Yeah.
And the two.
Sure.
Is that anything more than just assumption?
No. So the way we define the galaxy ellipse, it's just a stretch in the figure that basically makes you think something is on the galaxy versus off. But technically how we define the size of the galaxy is when the contours, the surface brightness contours, drop to a certain faintness level. So when the surface brightness contours go down to 25 mics per square arc second, we assume that's the radius of the galaxy. So within, and usually for all the calculations that I do, because there's this halo population which could be interesting, I always multiply that by a factor of 2. So both of those transients are safely within the 25 max per square arc second ellipse that we draw for these galaxies. If you just change the stretch, you see it's brighter here. You can't pick out the halo as much because it's very
The optical,
right.
that's only the central part. And you don't really see
Right, you can't pick out the halo because the central part is so bright that if you look at the stretch in the image, it looks like the galaxy is only in the center. But these are safely within the halos of the galaxies. A significant fraction, I would say about 10%, is simply because previous spectroscopic searches such as 6DF and things, looking down on the galactic plane is just so much confusion, there's so many sources, it's impossible. So about 10% or so, but still there's about 40% that can be done at high galactic latitude, which just hasn't been done because a spectrograph on a 4-meter telescope that surveys a huge area of sky is just not there. I mean, the best thing we had was SDSS, but that was only 8,000 square degrees. The total square degrees in the sky is 42,000. Narrowband filters. So we just got money to buy 2 filters, but these filters are not yet here. They're in engineering. They're still with the engineers. So maybe end of the year we should hopefully have 2 filters. But they're very expensive because their filters are literally this big. And they need to be interference filters because of the Schmidt design of the telescope. So, but hopefully end of the year we can start this project at least with 2 filters. And if we get more money, then a few more.